So I'll start talking, and then we'll see. Okay, so good morning. We start our fourth day of our school, school in Física Matemática. And today we have our first lecture by Luiz Agostinho Ferreira. Luiz Agostinho did his PhD back in Imperial College with David Olive, and he came back to Brazil, stayed for some time at UFT in São Paulo, and then moved for good to San Carlos, where he remains till now. Very active in many different fields, but let's say like general area of quantum field theory, integrable models. And today he will start with his first lecture on hidden symmetries. So he will find for us hidden symmetries. Okay, so Luiz Agostinho, your floor.
Okay, thank you very much for the invitation. It's a great pleasure to be here in this school. I want to congratulate the committee for the organization and following the lectures, and it's quite good. Today, what I'm going to talk about on these two lectures, so it's a short course on hidden symmetries. First of all, by hidden symmetries, what I mean are symmetries of the physical system, which are not systems of the Lagrangian, the equations of motion, Hamiltonian, so they are not split symmetry of the theory, but they are symmetries in some other sense that I'm going to explain. So I prepared the lectures to cover the broad audience we have. So I will start with very simple things in classical mechanics, one particle in a potential, okay? And then I'll move on to more complicated system. And then the goal is to talk about the hidden symmetries of gauge theories in 4 dimensions, right? Which is not a model, it's a physical theory. And so these are, I will cover in these 2 lectures. You can ask questions whenever you want during the talk, right? But if the question is too long, then we leave for the discussion section this morning, right? Okay, I'll share my screen and okay. So the hidden symmetries we are going to talk about, they relate in a quite nice way integrable field theories, especially 1+1 dimensions, right? To gauge theories in 4 dimensions. Everything I'll talk about will be at the classical level, right? The quantum level is something else that we plan to study, but I will not cover in these 2 lectures, right? As I said, they are symmetries of the system, but not of the Lagrangian or equations of motion, right? And they appear in a quite general setting in all these theories, from systems in classical mechanics, Newtonian mechanics, then field theory in 1+1, 2+1, and 3+1, right? So the main idea is the following. The equations I'm going to talk about equates a flux to a charge in a given volume or hypervolume, whatever. So the idea is you have a surface or a hypersurface, and you calculate the flux of some quantity here, and that's equal to the charge inside the volume bounded by that surface, right? The thing is that this equation, right, it's a conservation law, and it leads to an isospectral evolution for some operators in this form, right? So the eigenvalues of these operators are conserved in time. The thing is that is a known method conserved charge, in the sense that it's not a symmetry of the Lagrange. In fact, from what I know, the symmetries important for nonlinear phenomena are not nether symmetries, right? They are hidden symmetries because they appear in the system in a way it's more subtle and brings structures that are very important for the integrability of the model, right? These equations, they underlie gauge theories, because you know the integral equations of Maxwell's theory are of that form, right? And I will show you how to obtain those integral equations for non-abelian gauge theories, which have not been constructed until recently, right? And underlies integrable field theories. I will phrase the things in a way that what you know about integrable field theories in one dimension can be written in that form, flux equals to charge, right? And then at the end, I will talk about the integral equations for Young-Mills, which generalize the integral form of Maxwell's equation, and solve a long-standing problems of the conserved charge of Young-Mills theories, right? Which the ones which are constructed from Noether theorems, they're not really gauge invariant. So let's start then with a very simple example, right? Which is classical mechanics. So hidden symmetries in a nutshell. So, you know, you have conservative forces in classical mechanics, and the special thing is the following. Given the force, you can calculate the work done along an arbitrary path. It doesn't have to be the classical solution of the Newton's equation, right? You can define the path, the work as that integral. But for the conservative forces, the work has to be independent of the path. So if you change the path, keeping the endpoints the same, right? The work has to be the same. So this allows you to define a function, right, on space, which by choosing a reference point P0, you can stamp on every point of space a number, which is an energy, 32 ergs, 34, and so on, which is this in minus this integral, in fact, which is the potential, right? So you can stamp that number on any point of space, irrespective of the path you choose to go from P0 to P. Since the integral along gamma prime and gamma are the same, you can inverse one of them, and then you have a closed path. So the other way of phrasing it is that the work done on a closed path is zero. But by Stokes' theorem, the line integral along a closed path is the surface integral of the curl of that force. So statement, and you can think of this curve as a flat connection. So the components of the force can make a flat connection, right? Now, using the work done through now the path that solves the Newton's equation, we know that's a theorem, that's the variation of kinetic energy. So if you use that, you have the conservation of the mechanical energy. So using the fact that force is conservative and this theorem, you get that. Okay. That's just to phrase the thing. But now let's try to get this energy as an eigenvalue. Okay. So take this matrix, right? P is the moment of the particle. I'm talking about one particle in a potential, right? In one dimension. And then a function of the coordinate Q. if you calculate the eigenvalues of this matrix, what you get is that the square of them is p squared over 2 plus k squared over 2. If you take k squared over 2 as the potential, that's the energy, right? So that's just a trick, right? You build the matrix such that that happens. But the question is, this has to be conserved. Then these eigenvalues have to be conserved. So this matrix has to evolve in time through an isospectral evolution. Okay, you want that. So you have to find a matrix U that gives you that. So if you take the time derivative on both sides of this equation, you get the Lax equation, which is this one. And you have the, let's say, the Maurer-Cartan form of this matrix U, right? Now, if you choose this matrix U such that du dt U minus 1 with a minus sign is this matrix, and plug it there, what you get is that it becomes proportional to one matrix, it is sigma 3, right, times Newton's equation. So whenever Newton's equation holds true, that's 0. And if that's 0, that equation holds true, and then A has an isospectral evolution, and that eigenvalue is conserved in time. Okay. So here you have a hidden symmetry. That's the first one that we are going to talk about, because now you have phrased the dynamics of this system in terms of 2x2 matrices. So you have this gauge symmetry based on the group SU2, right? So A transforms like that, and B in this way, like a gauge field, okay, that's in one dimension. Okay, this symmetry you don't see. It's not a symmetry of the Newton's equation, right? It's a symmetry that appears when you phrase the dynamics in terms of these matrices. Okay. Now, what's the use of this symmetry? Let me show you how you can solve the system using this hidden symmetry. The first thing, you play a trick. You introduce a fake variable, x, and nothing depends upon x. Okay, it's still just time. But you take that two matrices A and B and make a connection, AX, AT. So in 2 dimensions, let's say. So the Lax equation you had becomes the curvature of that connection. So you have a flat connection in this fake space, X and T, right? Now, you can build the Wilson line for this connection, right? That's the definition of the way the Wilson line, giving a path. You integrate that equation along the path. You parameterize the path by sigma, right? And you get the Wilson line. And the formal solution is this one in red. Right? Just take the time, the derivative with respect to sigma. You can see that this is a solution of that thing. Right? But the point is that if you take the Wilson line now, defined by that equation, and vary the curve, okay, the variation of the Wilson line times the inverse of it is this integral, which is the integrand is proportional to the curvature of that connection, but by Newton's equation, that curvature is 0. So the Newton's equation implies that this connection is flat, as we had before, but more than that, the Wilson line is path independent. You can change the path and the Wilson line doesn't change, as long as you keep the endpoints the same, right? So if you want to integrate the Wilson line, you can choose any path between 2 given points, let's say the blue one, right? The way I order the Wilson line is from right to left. So you integrate on this vertical path, you get the integral b, which is the time component. And then along that one is at. But nothing depends upon x. So that's just t times at. And the same for the red one, okay? So what you have is you call u this integral of b, right? The path order WB, you get back the time, the isospectral evolution of A. Okay. So we have built a Wilson line operator for this classical mechanic thing. Now, the general solution is quite simple to construct. Since any path gives the same result, choose this one, and then the Wilson line is this thing. W of 0 is the integration constant, right? Then you integrate along the horizontal path, along X, nothing dependent on X. And then on the vertical one, you get this one. I call this one U, so you get this thing. But note that the A is Hermitian, right? And B, it's anti-Hermitian. So U is unitary, right? Because the exponent, the path order of that thing. So if you take the transpose complex conjugate of W and multiply from the left, you kill the U, right? And you get that this X is given by this one. So it's the integration constant conjugating this exponential of A0 times T, right? So you have solved the thing because the time dependence is explicit here. Nothing depends upon T. And you have written the solution in terms of this matrix X, which is the Wilson line complex conjugate times itself. Right? Now, you can see that this X parameterizes the phase space of your system. Okay, the way to see this is this thing. So the A0 and W0 contain the initial data of your trajectory. Right? So write the matrix in terms of the SU2 generators, right? And you can observe that there is an automorphism of order 2 of this algebra that leaves A odd and B even under this automorphism. So U is invariant. Okay. So if you take the U back, you can construct this quantity, which is W multiplied by sigma acting on W inverse from the left. Right? And if you do this and use the fact that U is invariant, you get this quantity, which is essentially what we had before. But now is not the complex transpose conjugate, but the inverse of the sigma acting on W0. Okay. But note that this thing is what people call the principal variable in an asymmetric space. Okay. So if you multiply W by an element of the U1 subgroup generated by T2, which is the invariant subgroup under the automorphism, okay, this X doesn't change because since age is invariant, the sigma cancels out, like U has cancels out here, right? Because it lies on the U1 subgroup, okay? And then this X is what's called the principal variable of this symmetric space SU2 over U1, which is two-dimensional, and it is the phase space of your particle, right? One thing. So that's another way of integrating this system, okay? That's a very simple example, but it contains a lot of ingredients that we are going to use in the more complex system we are going to treat, right? You can generalize this to mechanical system with more degrees of freedom, right? Then the symmetric space here is going to be the CPN. In fact, this is CP1, the complex projective space, and you can go to CPN. And so the structure is there. So what we have done is used the hidden symmetry of this mechanical system to construct a solution that you know very well, but in another way, okay, that is going to be useful in what follows. Okay. So the next system is a two-dimensional system, and it's a pendulum, you see, arranged in a line, okay? And they are connected, you see, by torsion. You have something, what's holding them together here has a torsion force. There's a torque on this thing. So again, we take Newton's equation for this system, and the first force that you have is a gravitational force acting on the pendulum, right? And the other one is the torsion, okay? So if one pendulum moves with respect to the other, there is a torsion coming from that thing, linking them together, and you have this thing. So if you call theta of xi, and xi is the coordinate of the pendulum on that horizontal thing, and delta is the spacing, of course, this force here makes a second derivative, right? It's the discrete version of a second derivative along the x variable running on that line, right? But you have already a second time derivative there. And if you take the limit such that the spacing goes to 0, but the constant given the torsion goes to infinity in such a way that delta square alpha is finite, you get the sine-Gordon equation, okay? So that's a mechanical version of the sine-Gordon equation. And this C here that plays the role of the speed of light is this quantity here, alpha delta square over, and L is the length of the pendulum, right? And omega square, which like a mass, right, is G over L. Is the period of the pendulum without the torsion, okay? Now, there are two regimes, there are many, but the two important ones for this equation. The first one is small oscillations, right? So if you look for small oscillations, so sine theta is theta, this becomes a linear equation. And the solutions are waves traveling along this curtain of pendulum, let's say, right? And K plays the role of the momentum of these waves. Omega is the frequency, right? And in capital of omega is the energy, right? So these are the plane waves, let's say, for small oscillations. But if you look for the other region where you can have big oscillations, right? You have this Soliton solution, which is the kink, the famous kink solution of sine-Gordon. And it's an exact solution, it's 4 times the arctan of this exponential. It travels with constant speed, v, right? And this is the profile of the angle theta, right? It comes from 0 here, there's a flip and then 2 pi. And the thing is that it travels with constant speed, but in a funny way, because as the pendula fall under the action of gravity, it decelerates, not accelerate, right? In such a way that it comes down here at rest. So as the kink pass, the curtain here remains at rest, because what you would expect that it would oscillate, right? Some oscillations would be left here. That's what happens in an ordinary system of like this one. But this one, no. So the energy is not lost. So the kink remains with the speed v, because if you had left some waves behind, it would decelerate and it would come at rest at some stage. So it propagates without dissipating energy. And if you collide 2 of them, and that's a much more complex thing, they don't destroy itself. They just suffer a time delay. Okay. And then you have a topology, because you cannot undo this kink, right? If for instance, you have proper boundary conditions at the ends of this line, right? Like being fixed at the walls, right? And the thing is, when you quantize this theory, the excitations I talked before, which are the small oscillations, they are described by the theta field. They are excitations of the theta field, right? But you are in the weak coupling region. But when you go to the strong coupling region, the mass of these excitations becomes small, right? Another important thing here is that the mass of this excitation is inversely proportional to the coupling constant. So in the weak coupling regime is very massive and very hard to excite them. And the strong coupling, they become, they have a very small mass, and so it's easy to excite. And it's better to describe these excitations in terms of the Turing model. In fact, they are the excitations of the fermion field of the Turing model. So it's a duality between Psi-Gordon and Turing model that was shown by Coleman long ago, right? So it's one quantum field theory which is actually solvable, right? Now, classically, what's the magic of these solutions, right? Again, you can write the dynamics in terms of matrices, okay? You introduce a matrix A0 and a matrix A1, right? And in diagonal here, you have the space derivative, and there is the time derivative, and then you have the exponentials of theta. But pay attention that you have a parameter lambda here, which does not appear in the model, but you can plug it there because it doesn't affect what you want. If you calculate the curvature for this connection, like we did in the mechanical system, Newtonian mechanical system, you get again the same matrix sigma 3 multiplied by the sine-Gordon equation. So whenever the sine-Gordon equation is satisfied, holds true, this connection is flat, right? So you have a gauge symmetry, because if the F is 0, any gauge transformation of it is still 0, right? So that's a symmetry of this system, which does not appear in the equation of motion, right? Not in the Lagrangian or Hamiltonian, but it appears when you phrase the dynamics in terms of this matrix, right? And the symmetry, the hidden symmetry here is a loop algebra, because this parameter here can be arbitrary, can be even complex. So in fact, you don't have just a pair of matrices. You have an infinite number of pair of matrices for any number, for any value of lambda. So you can phrase these algebraic structures in terms of the loop algebra, which is just multiplied by the SE2 generators by powers of lambda, right? Or polynomials of lambda. But the important thing is when you add a central extension to this algebra and promote it to the cat-smooth algebra, right? Then the representation theory of this algebra is much more complex and richer than this one, right? In fact, here you can have unitary representations, okay? And you can use this cat-smooth algebra to solve exactly the system. So this hidden symmetry does not appear in the equation of motion. It's important to solve the system, and you solve exactly the same way with the path independence, right? Which I'm going to show you now. So the fact that F, the curvature is 0, the Wilson line is path independent. It's the same reasoning I used in the Newtonian mechanical system. So what you do is this. Now you have a true two-dimensional space. It's not a fake system, it's space like in the Newtonian mechanics. And let's take these 2 points, x minus L and t equals t, and x equals L and t equals t. I will take this L to infinity at the end, right? And I choose these 2 paths, just straight, and then like this U form path. So since it's path independent, the two integrals are the same, the two Wilson lines are the same. But to get the conservation, as usual, you have to impose boundary conditions. So impose that the time component of the connection is periodic in x equals ln minus n. Right? So then you get, again, an isospectral evolution that the Wilson line calculated on this path is the Wilson line calculated in the same path at t equals 0, conjugate by this matrix U, because the integral on the vertical axis here, due to this boundary condition, is the inverse of that one. Okay, so that's the U operator. So then the eigenvalues of these operators are constant in time. But remember, this A depends upon lambda. So you can make a power series expansion in lambda here, and you get an infinite number of conservation laws for this thing. And that's what makes it integrable, right? So this structure that appears in sine Gordon, it's what appeared in any soliton theory in 2 dimensions, right? Any equation that has exactly soliton solutions in 2 dimensions, I know of, have this structure, this zero curvature or Lax equation or Lax-Sakharov-Chabat equation, right? Which is the curvature is 0 for this connection. And here I show a picture that was taken in Glasgow in 1995 to celebrate the 100th anniversary of the Korteweg-de Vries equation, which described waves in shallow channels like this one. And it was first discovered there in Scotland in the 19th century, right? But the equation was written down by 2 Dutch guys, Korteweg and de Vries. And that's a conference. Kruskal is here, though a lot of people that have contributed to this thing. So that's a quite well-established area of mathematical physics and physics. And everything can be described by flat connections on Katz-Mood algebra. Okay. And another way of phrasing it is that you have a linear problem, right? And the integrability condition for that linear problem is the flatness of this condition, the curvature should be 0. Okay, that's the original formulation of this thing by the Leningrad school, by the Sato school in Kyoto, and others. And so you have infinite number of conservation laws for this thing. There is the inverse scattering method to solve this linear problem. Another version is the dressing method, okay, or the Rota method, which is a much simpler version of these things. And you have much sophisticated structures in this thing, which is the classical R matrix. Okay, I won't have time to talk about these things, or the quantum R matrix. And this nowadays plays an important role in this connection between correlation functions in super Yang-Mills theories with 4 supersymmetries in 4 dimensions, and statistical mechanical system like spin chains, right, which are solved by this Yang-Baxter equation. Okay, and this connection has been explored a lot. Okay, and that's why lies behind the connection between integrability and supersymmetric Yang-Mills theory in the context of the ADS-CFT conjecture, right? So that's the structure. Okay. Now, this has been developed in the last 50 years, I'd say, or more, 60. And as I said, it's a quite well mature and established structures in mathematical physics. There is a very rich mathematical structure that allows all these magic things to happen. Right? Now, the question is, if you want to go to higher dimensions, right, beyond 1 plus 1, things change drastically, right? And here comes the question, how to find the charge for field theories in dimensions higher than 2, right? This question has been trying to be answered in many ways, okay? But I'll show you one with Mr. Holmes has told me, okay, which is the following. In 2 plus 1 dimensions, we should expect the charge to be integrals over 2-dimensional surfaces, right? So take a surface sigma, right, with a border gamma. So the charge would be integrals along surface like this. That's what you expect. The Noether charge, for instance, field theories in 2 plus 1 are like that. But as I said, Noether charge usually are not important for the solvability of this theory, right? So if you scan a surface, let's take a point on the border of this surface sigma, right? And scan it with loops, starting and ending at the point x0 on the border, okay? There is an infinite number of ways of doing that, okay? But a scan is such that any point belongs to one and only one loop, so the loops don't cross, right? So you can scan the surface with loops, so you can think of this surface as a sequence of points on this functional space, which are the space of maps from the circle S1 to the space-time, such that the north pole of S1 is always mapped on X0. That's this famous loop space, right? It's the first loop space I'm going to talk about. I will generalize to other ones, right? So if you do that, you can think of this surface, right, as a path in loop space, because this point x0 here is the infinitesimal loop around x0, and then every loop there is a point here, because that's a function on this space. So any point here in loop space is a function. So you describe one loop there. So, and the end point is the border of this surface. So you have a path in loop space, okay? So you have flat connections in space-time, right? So the idea is to introduce a flat connection in loop space. That's the first thing you can think of, right? Now, note that in 2 plus 1 dimension, you are using this loop space with the maps of S1 to M, okay? If you go back to 1 plus 1 dimension, right? So you have already a path in space, but you can think of that path as a path in loop space, which are the maps from S0 to M. What is S0? S0 is just x0 squared equals 1. So is x0 equals plus minus 1. So it's just 2 points, right? Since you are fixing 1, so the loop space is isomorph to M. So the omega 0 loop space is isomorph to the space-time, and that you have that. Three-dimensional space, right? So the idea is this: you construct the charge from this flat connection on loop space. The question is, your field theory doesn't live in loop space, okay? So you have to build this connection from things in your field theory. So the first thing you can think of is this: you take a rank 2 tensor, B mu nu, right, in space-time, and a connection A mu, right, on on space-time. So that's W is the Wilson line for that connection. So you conjugate the rank 2 tensor B with this Wilson line. This is integrated on a given loop, so it's a point in loop space. So this quantity is defined on loop space, local loop space, right? And that variation here is perpendicular to the loop. So that's what to give a one-form character for this quantity A, calligraphic A. Okay. Now, the reason why I conjugate with W is because I'm going to apply the theories that have local symmetries, is the following, because this connection has a gauge symmetry with the transformed like that, and the Wilson line transformed like that is G at the end point on the left and the inverse of G at the initial point here, right? So when you conjugate B with that, and if B transformed by conjugation, like in the adjoint representation, it doesn't really have to be the adjoint here. I can give examples where it's not, but it still transforms on the conjugation, right? So what happens is that that local symmetry becomes a global symmetry. So this A here, you kills the local symmetry of this connection in space-time, okay? And this makes easier for you to preserve this local symmetry in loop space. Because if the integrand here would change under gauge transformation in space-time, it would be a mess, right? So then I make this local gauge symmetry in space-time a global symmetry here on this connection. But now I'm going to have gauge symmetries on loop space-time, right, which are much bigger. And I'll use this notation. Whenever you have a upper index W here, it means I'm conjugate the quantity with the Wilson line this way. Okay. Now you calculate the curvature of this quantity, right? That's because that's what I want to be 0. So if you calculate the curvature of this connection, you get this thing. You get here an integral on the loop, which is the exterior covariant derivative of this rank 2 tensor, and the covariant derivative here is in the adjoint representation, is this one, right? With a double integral on loop space, but it is the same loop, right? With a commutator which involves the B's and F's, that's the curvature of the connection in space-time, right? Which is these funny combinations B minus F conjugate with the Wilson line and then commuting with B. That's a funny thing, but it appears whenever you take these connections in loop space. In fact, people working category theory get that. So then what you want is that you define a field theory where these B and A will presumably depends upon your fields, and you want the equations of motion to make this connection 0, right? But the problems start here. To have F equals 0, this condition is local in loop space, right? Is non-local in space-time. So you have some difficulties, not some, a lot of difficulties to describe local field theories through this formulation, because that's a non-local equation in space-time. Is local in. For some time, we thought that integrable theories in higher dimension would be non-local theories, right? Could be defined on this space only. There is another problem here, which is quite serious, which is this following. Given a surface in space-time, there is an infinite number of paths in loop space that correspond to the same physical surface. So you have a reparameterization invariance problem here. At the end of the day, your results have to be independent upon the path in loop space you choose to describe that particular surface, right? So it's quite hard to reconcile with local field theories. However, you can simplify things and get local conditions. I think we have a question.
It's me, Luiz.
Yes.
I'm a little confused because SU2 appears in a very natural way in the examples you showed us in the beginning. What's
Yes.
the underlying group now?
Okay, that's exactly what I'm going to talk about.
Because, I mean, is it right to think that SU2 appeared there in a natural way because of the dimensionality?
No, when I discussed those two examples in the Newtonian mechanics case and the 1+1 thing, I used the example of SU2, but you can do it for any Lie group. For instance, you have, take the total field theories. You have a total field theory. In fact, you have many total field theory for any Lie algebra. In fact, any cut-smooth algebra. It doesn't have to be SU2 only. For instance, you have the SUN total field theory. Then you have the SUN cut-smooth algebra, right? And then you have many fields, not just one, like the sine Gordon. So you can have a E8 total field theory, or have a, well, there is a connection between the Ising model and E8, right? It's a very interesting connection. So I kept SU2 to make things simple, right? To have 2x2 matrices. But I forgot to say that you can do that for any Lie group or any loop group, in fact, any cut-smooth group. Okay. That's another thing I haven't said. That the structures that appear there is the cut-smooth group that's not quite well understood yet, right? In fact, just since you asked, you can treat the Lie algebra, you can treat, that's well done. But in the group, you are exponentiating an infinite number of generators, and there is a problem of the convergence of the exponential map, okay? Katz, Victor Katz, have shown that if you have an integrable representation for this group, and this integrable has nothing to do with the integrable field theory, it's integrable in the sense that the operators of the Lie algebra, so the cut-smooth algebra, are nilpotent. There is some power of it, which is zero. Then the exponential map truncates to some order. And then you have a polynomial and not an infinite series. And then you can sum. And then the group element in those representations, that's called integrable representation, are suitable to treat these groups. So you have a groups in a given representation where you can make sense of it. And this funny thing is that the realization of this representation is in terms of vertex operators. The vertex operators that appear in string theory, in many condensed matter physics, like the quantum Hall effect and so on. Let's take the Fubini-Veneziano vertex operator, right? It's the simplest example. And they lead to this integrable representation. And the funny thing is that they lead to the integrable system. These soliton solutions are constructed in this integrable representation of cut-smooth algebra. So then the two words integrable, in the sense that the exponential map truncates, and integrable field theories get together through this vertex representation of cut-smooth algebra. Okay. Now, coming back here, as I said, you can simplify this thing. In fact, you kill most of the structure, but you can still do something which is interesting, which is this. You take the connection A to lie in any Lie algebra, let's say finite Lie algebra, and you take B to form an abelian subalgebra of this non-semi-simple Lie algebra. This is like the Poincare algebra, like